Hey, this is Brock Lemires, and in this video I want to start looking at circuits that contain diodes, and more specifically a circuit that contains an LED, okay? All right, so we've learned about diodes and how they work, and we've learned about the constant voltage drop model for analyzing circuits with diodes. And in what I want to do now is I want to build this circuit that has a DC voltage source and a series combination of a resistor and a diode. And what I want to do is I want to build this on a breadboard, and I want to do some calculations on what I expect to see in terms of the voltage across the resistor, kind of extract what I think I'm going to see in terms of voltage across the diode, and then do calculations using the constant voltage drop model and figure out what the current's going to be. Okay, so I want to basically calculate and verify by measurement. Okay, so here's my breadboard, and what I'm going to do is I'm going to have my power supply is going to be my 9-volt battery. I've got a diode right here. This is an LED, okay, so a light emitting diode. And LEDs are really cool to use when you build diode circuits for the first time because it's really obvious when they turn on, right? If they turn on, they light up, okay? So a normal diode doesn't light up, and so the only way you can tell it's on is if you measure its current. But an LED will tell us immediately when the voltage across it is sufficient to meet the forward voltage requirements in order to let current flow through it, because you'll see the color red, okay? And then I have a resistor right here. And so let's take a look first at the data sheet for this diode and see how this thing looks, okay? So here's a data sheet for this diode that I'm using. It's just a standard 5mm red LED lamp, and got dimensions and everything on here. And when you scroll down, you start seeing the first table of like what are the absolute maximum ratings. And the maximum forward current, meaning that the current that flows from the anode to the cathode when this thing is forward biased or normal operation, is 20 milliamps. So you don't want to go above that long term, or else you can damage the device. We'll actually put a little bit more through it, why not? You can also pulse a higher current. So this spec right here says you can go up to 60 as long as you pulse it like 10% of a 10 kilohertz wave. You could do that. But anyway, that's kind of just the order of magnitude you're seeing. It's not going to be amps that go through this LED, but it's also not like nano amps either. It's not that small. Scrolling down, you see the forward voltage. So it's saying that if you're, running about 20 milliamps through this thing, your forward voltage is going to be somewhere between 1.7 and 2.6. So it's quite a big range. We'll use 1.7 as a starting position, and then we'll actually measure the forward voltage depending on different current levels that go through it, and we'll use those in our calculations. And then one of the things you're going to see here is there's these plots that kind of show, voltage versus current, but of interest to us, though, is with an LED is actually how bright it is versus current. So this plot right here shows your forward current versus relative intensity. And so if you think about like your current at 1 milliamp, it's like it's that intense, and then at 10 it's that, and at 20 and it goes up, 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 up. This plot shows you that as you increase the current through it, it becomes brighter and brighter. And at some point it just won't get any brighter. You're basically outside of its operating realm. But that's basically what how these things work. More currents means brighter. Now this is an interesting plot because it shows you the relative intensity versus wavelength. This diode has materials in it that emit photons with a specific wavelength. So it's only going to be red. It's not like you're going to put a bunch of current through it and this thing will turn green. It's like, no, the materials in this thing will only emit red photons. So this is a red LED. Okay, so let's take a look at some initial calculations of what we're going to do. So let me get the breadboard out of the way here. And what I'm going to do is I've created this nice little table here to kind of tabulate what I'm going to be doing. And if you look at this, what I have here is I've got 3 circuits. We'll just look at circuit number 1. But what I do is I have kind of nominal values for the circuit that we're building. And the power supply is going to be 9 volts coming from my battery. R1 is going to be, let's start with a 150 ohm resistor. And then the forward voltage will be 1.7. But I want to first measure these, and then I'll use those in a calculation to determine the current through the circuit and then also V1 across that resistor. All right, so let's think about this though. The resistance, we want to measure that, but you can't have it in the circuit. You have to have it by itself. And so let's do that one right now. So I'm going to there's my resistor right there. I'll grab old trusty, bring it over here, and I'll go ahead and fire that up into resistance mode. And I know I'm looking for about a 150, so let me turn that on, clip, and we'll see what we got. And it turns out that we have about 148.8. Let's call it 149. Okay, so I got 149 ohm resistor. That's within nominal, no worries. So I'll go ahead and put that down here. I'll do it in red so you can see it. So we're at 149 ohmer. Okay. Now we're going to measure the 9-volt battery and the forward voltage, but we have to actually do it with the circuit powered, because remember, once you start pulling current through or current out of a battery, it isn't exactly 9 volts. So let's come along, and here's our breadboard now, and here's our battery, and now let's build up the circuit. Well, it turns out it's pretty easy when you build a series circuit with an LED, because I have my power supplies routed throughout the breadboard, so all my red rails are 9 and all my blue are connected to the negative terminal, or what we call ground. This particular LED has a longer lead indicating the anode, so that's how I know that the anode is this one and the cathode is this one. And so what I'm going to do is I'm actually just going to plug the cathode into ground and then the anode into a terminal strip. And then all I need to do is essentially come along here, and I'm going to put my 149 ohm resistor into the power strip, and I'm going to put it in the same terminal strip, and now they're in line. And now when I power this thing up, if I have enough forward voltage across that thing, it will light up, and lo and behold, look at that, I got it. So I have a red LED going. So it's like, okay, that's pretty sweet. Now let's take some measurements and complete our table. So I'm going to come back over here, and the first thing I want to measure is I want to measure some voltages. So let's go ahead and measure the power supply. So the power supply is going to be across the entire series combination of these. So if I touch that, I've got 8.3, holy moly, so that's dropping like crazy. So I got 8.3, and then across the diode I have 1.95. Interesting. Okay, so 8.3 and 1.95. Good old trusty over there, and then let's enter those into my table. I'm going to unplug the battery so I don't drain it because it's getting a little low. So I'm going to come back here, and I got 8.3 volts, and I got V forward of 1.95 volts. So now I want to do some calculations. How can I calculate the current and the voltage across the resistor using the constant voltage drop model? So let's think about this. The first step when you think about the constant voltage drop model is this. Is it on? All right. And the answer is yes. And you go, well, yeah, I saw it turn on. But in reality, you can look at this and say, okay, the entire 9 volts, or in our case, 8.3 volts, is going to be across a series combination of a resistor and a diode. Is there enough voltage across this series combination to provide the forward voltage to the diode? And the answer is absolutely, because it's higher than the forward voltage. So we will be able to put 1.95 forward voltage across the diode, and the rest of it can go across the resistor. So the answer is yes, it is on. Why was that important? Well, it's because I can now draw the right model. So then the model of the diode is where you just draw a constant voltage source. So now what I'm going to have is I've got plus and minus, and this is 8.3 volts. I've got a 149 ohmer resistor, and then I have my diode model, which is this, and it is 1.95 volts. So now when I come along here, what I'm trying to do is I'm trying to solve for the current, and I'm trying to solve for the voltage across that, V1, and it's like, how can I do this? Well, this is actually pretty easy, because if I do KVL around this loop, what I get is I'm going to sum my voltage rises, which is over here. I go from negative to positive on the 8.3, so I'll put my rises over here on the left-hand side of the equation, and then I'll go from plus to minus across the resistor, so that's a drop, so I'll put V1 over there, and then I'll drop across the diode, which is 1.95. Immediately, I can solve for V1. So V1 is nothing more than 8.3. Let's subtract 1.95 from both sides of the equation, and we will get V1. So here we go. Let's bring out a buddy and go 8.3 minus 1.95, and I end up with 6.35 volts. So that is the first thing that I've looked at. So I calculated, so it's 6.35 volts. And then the current is actually trivial, because I know what the voltage is across a resistor that I know the resistance of, and so I can simply do Ohm's law, and so I'm going to say V1 is equal to I multiplied by R1. So I can say, okay, V1 is 6.35 volts, and then I've got I, and then I have 149. So I is going to be equal to, divide both sides by 149. So I'll take 6.35 and I'll divide it by 149. And I end up with 42.6 milliamps. Okay. Now you're immediately going, wow, that's pretty sweet. Let's verify that though. So 42.6 milliamps. Okay, now I want to verify it. All right, so let's go ahead and bring back our circuit. And here we are, and I'm ready to bring back old trusty, and let's fire it up and do the voltage measurement first. So we think that the voltage across this resistor is going to be 6.35. So let's go to, here you go, and let's see where we're at. So let me clip on here, turn on the light, and I end up getting 6.35 on the money. That doesn't happen all the time. Okay, so let's go in here and let's go 6.35 on the money, 100% accurate. Okay, now the current. We think we're going to measure 42 millis. So now remember, I'm gonna do current here. So I gotta change my. Let's see. I'm gonna go into. Where's current? Oh, there it is. So current, it's going to be below 200 milli, and I need to break the circuit. So let me break it in between the diode and the terminal strip. So or the resistor. So when I do that, look at what I got. 41.7. Okay, so 41.7, not bad. 41.7. So let's write that down. 41.7 milli. All right, and it's going down. You're like, why is it going down? It's like, well, it's actually 41.8. Pretty dang close to 42. Why do you think it's going down? I can tell you exactly why it's going down. It's because my battery's dropping. But that's all right. Pretty dang close. What's even more cooler is that I was able to calculate what I was expecting, and then I got it almost exactly. So this constant voltage drop actually works. Okay, this is great. Let me show you one other kind of interesting thing. Let's look at the difference between the same LED. Okay, so I have a couple other LEDs, and I'm going to put these in there, anode to cathode, and I'm going to put anode to cathode right here, and I'm going to light these up with different resistor values. So let's come along and compare that to if I did a 1K. So I'm going to put a 1K in here, and it is enough to turn it on. Okay, so it's like, oh, okay. And then let me put a 10K in here, and let me put a 10K into here, and now you ask the question, is that thing on? It's like, boy, that isn't too bright. Let me turn off the lights. It's like, let me put paper underneath it so you can kind of see it. It's like, is that thing on? It's like, it is on. It's hard to see though. I mean, it's barely on. So can you kind of see that? Probably not. It is on just a tiny bit. And then this guy is on, but it's not quite as bright as this dude right here. This guy, 42 milliamps, this is out of spec. We're destroying this LED right now, but I mean, it's a pretty cheap thing. It's not going to hurt anybody. So we're destroying it in the fact that it won't last its entire lifetime because we're above the maximum rating. This one, though, is probably a lot less, and we could absolutely calculate it. But let me just show you one interesting thing. Beyond this being interesting, that as you limit the current by increasing the resistor, it gets dimmer and dimmer, right? But now let me show you the forward voltage and how much that changes. So I'm going to come back to voltage, and let me do this. And what I'm going to do is let me clip onto the ground right here, and then let me measure the forward voltage of all these things. So the first one was what we already did, which is 1.95. This is the 1K, 1.72, and then this is the 10K, 1.6. Our forward voltage is dropping when the current goes down. And it's like, that is nuts. That is crazy. Why would that forward voltage drop? Well, it turns out that that's just how diodes are. If you remember the IV curve, as you put a voltage across it and you look at the I, it goes like this, right? And so what you're thinking about here is as the current is lower, the forward voltage is basically just this knee right here. And as if the current's smaller, or the current is smaller, what happens is that you're seeing this right here. So this was like the 1 point, this was like the 1.6. This was like the 1 point, this was the big one, right? So it'd be like 1.95. And then this was like what was the last one we just did here? 1.6, 1.7, 1.95. So then this was like 1.6 right here and then 1.95. So it's different current values that are associated with these different forward voltages, but the constant voltage drop model gets us super, super close. It's just like, go for it. So usually what you do is you can kind of just build the circuit, measure the forward voltage for the particular operating condition you have, and then you can solve using the constant voltage drop model and figure out what your current's going to be and what your voltages are in the rest of the circuit. Okay, so that is it. We did it. We have built our first diode-based circuit. We have done some calculations using the constant voltage drop model, and then we verified our calculations with measurements. So nice work, and we'll see you.